constant strain triangular element, that is CST element. A three-noded triangular element is known as constant strain triangular element. It has 6 unknown displacement degrees of freedom. Here the triangle specified node number 1, 2, 3. It have two actuations, both x and y direction. We call it as u1 in the y direction, v1 in the y direction. We call it as the displacements. Likewise, we have to specify the terms in each and every node point of the element. For element node point 2, I can get u2, v2. Then u2 is the horizontal force displacement, v2 is the vertical y direction displacement. Likewise, we have to specify the point 3. u3 is specify horizontal displacement in a triangular element, and v3 is the vertical triangular element in the product or element. Shape functions for the CST element. Shape functions n1 is equal to pi plus qix plus r into xy, x by y into dA into a. Shape functions n2 is equal to p2 plus qx plus r2y by 2a. Shape functions n3 is equal to ng, n3 is equal to p3 plus q3x plus r3y by 2a. Displacement functions for CST element. Displacement functions e of x comma y, n0, n1 0, n2 0, n3 0. Then v of x comma y 0, n1 0, n2 0, n3. So you can make it as a triangular, you can make it as a vectors. So strain displacement matrix B for CST element, the strain displacement matrix 1 by 2 4. Actually, so q1 0, q2 plus 0, q3 0, and 0 r1, 0 r2, 0 r3. So r1 beta 1 r2 beta 2. This is the thing here. The things to be considered very much essential in as triangular elements. Why we prefer triangular elements? Any complicated steps means we can easily convert into triangular elements. So it's very easy to split up and we can make calculations. That's why we mostly preferred this triangular elements in finite element method. So strain displacement matrix beta b is equal to 1 by 2a, q1 0, q2 0, q3 0, 0 r1, 0 r2, 0 r3. So r1 q1, r2 q2, r3 q3. So where q1 is equal to u2 minus u3, so q2 is equal to u3 minus u1, q3 is equal to then r1 is equal to r1 minus r2, so r2 is equal to x1 minus x3, then r3 is equal to x3 minus x2 minus x1. Stress relationship matrix or a constitute matrix D for two-dimensional element 1 minus rho nu 1 minus nu 0 0 0 for first row, then second row nu 1 minus nu 0 0 0, nu 1 minus nu 0 0 0. Stress strain relationship matrix for a two-dimensional plane stress problem. Normal stress, so dz is e by 1 minus nu square 1 nu 0 nu 1 0 0 0 1 minus nu by 2. Stress strain relationship matrix for two-dimensional plane strain problems. Stiffness matrix equations for two-dimensional element CST. We can make it a CST element. Then CY is equal to so B is equal to stiffness matrix K is equal to B transpose DB A into D. So B is equal to 1 by 2A Q1 0 Q2 0 Q3 the temperature affects distribution of the change in temperature. Delta D is known as strain due to change in temperature can be considered as an initial strain. So sigma is equal to D into Bu minus C suffix D. Galerkin approach, stiffness matrix K is equal to B transpose D B A into D, force vector K into U.